Now let's take a look at some two-dimensional problem practice. Can the magnitude of the displacement of an object from its original position ever exceed the total distance moved? Well, for this we need to keep in mind what displacement is. Right? Displacement is going to represent change in position. So if, say, D1 is there and D2 is there, then our displacement is going to be a straight line from there to there. Okay. However, there we go. If, say, D2 is there and D3 is over there, now our displacement is simply D1 to D3. Something like that. Okay? And does not take into account D2 at all. So what can we conclude from that? Well, the distance traveled is always going to be a linear, in number, a calculated distance from D1 to D2 plus D2 to D3. Okay, so distance will always be greater than or equal to displacement. So the answer to this question is no. The displacement can never be larger than the total distance moved. Can the total distance moved ever exceed the magnitude of the object's displacement? Well, of course, that's kind of the opposite of what we just talked about. If that's D1, that's D2, and that's D3, and let's just say that's 2 meters, that is 2 meters, okay? So we would say that the distance equals 4 meters. The displacement, however, is simply shortest distance between the beginning and the end. And our displacement in this case would be something less than 4, maybe 3.2, let's just say. Okay? So, the answer to this question would be, the total distance ever exceed the magnitude of the object's displacement? Yes, it can, because distance is always greater than or equal to displacement. Question 3. Cheetahs, the world's fastest land animal, can run up to 125 kilometers an hour. So V equals 125 kilometers per hour. A cheetah chasing an impala runs 32 meters north. So we'll just draw that out. 32 meters. Then suddenly runs 46 meters west. Before lunging at the impala. The entire motion takes 2.7 seconds. So in this question we're going to be asked for determine the cheetah's average speed. Okay? So the average speed in this particular case is going to be distance over time. Distance is going to be the 32 plus 46 divided by 2.7. That's going to equal to 32 plus 46 equals 78 over 2.7, which is going to equal to 28.9 meters per second in this case. Okay, so we actually didn't need this value to begin with. The next question is very similar. Okay, in this case though, we are looking for the average velocity. So let's redraw our vectors. So we have 32 meters north. We have 46 meters west before lunging at the impala. Again, our time is 2.7 seconds. So now determine the cheetah's average velocity. Now, average velocity is going to equal to displacement over time. So we need to find displacement because we know time. Time is 2.7 seconds. Displacement is going to be this guy right here. Now, this is a right triangle. Okay, we know because he went north and then west. So the simplest way to do this question is simply use the Pythagorean theorem and solve for that. Okay, we don't have to do any other vectors. It's all pretty easy. So we would say that displacement is going to equal to the square root of 32 squared plus 46 squared and that comes out to be 56.0 meters. We also need to know an angle when we're talking about displacement. So theta in this case is going to equal to inverse tan, opposite over adjacent. So 46 over 32. So we hit inverse tan on your calculator. 46 divided by 32. So that equals to 55.2 degrees. Now we have two sig digs in our question, so let's write our final answer. Therefore, the displacement equals 56 meters. Now we're going north first, and then we're going west. So we say 56 meters north, 55 degrees west. Air molecules travel at high speeds as they bounce off each other and their surroundings. In 1.5 milliseconds, an air molecule experiences the motion shown below. For this motion, determine the molecule's average velocity. So, velocity, that's our question. We know time is 1.5 times 10 to the negative 3 seconds, because it's 1.5 milliseconds. And we got this motion here. So we need to break it into its vectors. Okay, so we need the x and y vectors for each. So for 1, for 2, and for 3. Okay, so let's break this down. So if I'm looking at the net x, we would say the net x is going to equal to, first of all, this guy right here. Okay, so we'd say x1 plus x2 plus x3. And now, of course, we need to assign a positive and negative, so let's do that here. And we'll say that is positive like that. Okay? So x for the first one is 35, because it's the entire direction is east, the entire vector is the x, so we say 35. For 2, we actually have 0, because you notice it's going down. There's no horizontal component, so it's 0. And then for the last one, for 3, it's going to the right, so plus 22. You add all those up, 35 plus 22 is 57 centimeters. Now we do something similar with the y. We say y equals, y equals y1 plus y2 plus y3. Now there's no y component in number 1, so we'd say 0. y2 is going downwards, so we say minus 15. And then 3 again, there's no y component, so we'd say plus 0. That gives us an answer of obviously minus 15 centimeters. Now, you need to draw your new triangle. We have plus 57 and minus 15. So we go right 57 centimeters, and we go down 15 centimeters. Down because it's negative. We draw the hypotenuse, and that's going to be our displacement. So like we did before, displacement is going to equal to the square root of 57 squared plus 15 squared, which equals 58.9. Now again, we have 3 sig digs in this one, so the correct answer is 58.9 centimeters. Okay, not quite done yet. Again, we need an angle. So theta is going to equal to tan -1, opposite over adjacent. So 15 over 57. Which equals to 14.7. So we would say in our concluding statement, therefore, the displacement equals 58.9 centimeters. So we are going east and then south, right? Because we have east and then south. We would say east 14.7 degrees south. How do VAB and VBA compare? I'm sorry, this didn't come out properly on this screen, but it should be V and then subscript. Okay? Now we talked about the 2 letters in regards to relative motion. Okay? We're always looking for the first letter being sort of what we are talking about, so the speed of this. So we could say, what are looking at and then the second letter is always going to be relative to. So for VAB, the answer to this question would be, what is the velocity of A? So we would say velocity of A relative to position B, right? That's VAB. And if we were saying VBA, we'd be saying, what is the velocity of B relative to position or object A? An airline pilot checks the instruments and finds that the velocity of the plane relative to the air is 320 kilometers per hour, 35 degrees south of east. Our radio report indicates that the wind velocity relative to the ground is 75 kilometers per hour east. What is the velocity of the plane relative to the ground as recorded by the air traffic controller in a nearby airport? So first thing we need to do is we need to write our formula down. We need to know that the velocity of the plane to the earth is always going to be equal to the velocity of the air to the earth plus the velocity of the plane to the air. Okay, now we're given a few things. Okay, first of all, that is our question. The velocity of the air to the earth, we're told, is 75 kilometers per hour east. Okay, and the velocity of the plane to the air is 320 kilometers per hour, 35 degrees south of east. And that's going to look like this. 35 degrees and 320 kilometers per hour. Okay, and our vector for this guy is going to look like that. So if we add that vector to this vector, tip to tail, as we always do, we can then start breaking apart this vector into its components. So we'll call this 1 and we'll call this 2. So again, we need to find the sum of the x's, the sum of the y's. So x, start with x. Okay, now x component is going to be that and that. Okay, so the x for number 1 is going to be 320 cos 35. And I forgot to write in my plus and directions. So we'll assign right to be positive. Okay, so 320 cos of 35 because it's the adjacent side. And then of course we're going to add 75 because this component is 75 kilometers per hour. We put that into our calculator. 320 cos 35 plus 75, and that equals to 337.1. We then do the y components. So the y component is going to be coming down. We said up was positive, therefore it's negative 320 sine 35. And in number 2, we have no vertical component, so it's just plus 0. So we put in your calculator negative 320 sine 35, and you get negative 183.5. That's an 8. So we draw it out. We have a positive 337.1. 337.1, and we have a negative 183.5. Our job is to find this. This is actually velocity of the plane relative to the Earth, because we are we're doing additive vectors. Okay, we had one vector here, number 1, we had one vector here, number 2. We added them together, and that gives us our hypotenuse. Okay, so as always, VPE is going to equal to the hypotenuse, okay, which is going to equal to the square root of 337.1 squared plus 183.5 squared, which is equal to 383.8. Okay, and of course we need to find theta, as always. Theta is going to equal to tan negative 1, 183.5 divided by 337.1, which equals 28.6 degrees. We would then say, therefore, VPE equals, we have 2 sig digs in our question, so VPE equals 3.8 times 10 to the 2 kilometers per hour. Now we're going east first and then south, so we'd say east 29 degrees south. A wind is blowing from the west at an airport at an east-west runway. Should airplanes be traveling east or west as they approach the runway for landing? Well, as always, okay, if this is the wind vector, okay, it says with an east to west runway, so the runway looks like that. Okay, now there's my plane. Okay, planes always land into the wind. They land into the wind so as to slow their descent. So since planes land into the wind, and the wind is blowing from the west, okay, northeast. If it's blowing from the west, it's blowing east. Okay, so since planes land into the wind, the plane should travel east to west to land.